Hello, good morning. So, are we ready for the class? Not many have joined in yet. I hope all of you heard our Prime Minister's message this morning. All right. We all are going to be very positive about this entire scenario. Yeah. So, now that I can see many students have already joined in, we are ready to begin the class. Okay. So, as you can see on our board, I have written down the particular topic that I am going to cover today. Fine. Yesterday, if you remember, we had derived the time-dependent as well as time-independent Schrodinger's equation. And today we are going to see how to apply this, how to solve one such example, solving this Schrodinger equation for a particular case. Okay. And thankfully, in our syllabus, the particular examples that we are required to solve are very, very easy ones. We don't have to do very complicated mathematics. This is for you all to understand how this calculation is done in quantum mechanics. Fine. So as you can see, we are going to solve the Schrodinger's equation for a particle which is inside something called a one-dimensional potential well. Now, I am going to explain what is the meaning of this one-dimensional potential well. But this is how the heading looks like, and this is how we generally denote the particular potential or the particular system that we are going to learn today. Right? Then, let me first explain to you what is the meaning of a one-dimensional potential well. Now, before we jump into the topic, let me just remind all of you that we had discussed yesterday that kinetic energy remains same for every system. However, what makes one system different from the other? It is its potential energy. And when does a system gain potential energy? When it does some work, depending on the force it is acted upon by, or depending on the potential it is acted upon by, right? So, this potential well that I have written down over here is the particular potential which the system, which this particle that we are talking has been imposed on. Fine. So, this particular potential is going to make it different from any other system. Even though its kinetic energy is going to remain the same, and hence its kinetic energy operator in our Schrodinger equation will look like the same term. However, this potential is going to be different and our solution is going to be different for this individual case. Fine. So first let us try to understand what is the meaning of one-dimensional potential well and why on earth are we using this term well in this case. Fine. So it is very interesting. Let's jump into our topic. So imagine we are dealing with a particle which has been trapped inside a potential well. Now, since this is one dimension, once again, let us think about the situation where the particle is only allowed to move along the x-axis. So, our particular dimension is the x direction. And if I draw the x direction like this, and then along the y direction, along the y-axis, we are going to plot the potential. Fine. Now, mathematically, how do we define this potential well? Please see carefully. We define this potential well as V, which is a function of x only. Remember, yesterday also we were discussing that the particular potential energy or potential depends only on the position of the system or the particle. And since we are moving along x-axis only, our potential will depend on the x value. So this potential is a function of x. So this is a very interesting potential. How does it look like? This potential Vx is 0 in the limit A. I will explain this. Just give me some time. First, let me write it down. Or in very easy term, let me just write it as elsewhere. Now, let me just explain to you what I have written mathematically in this particular statement. So, our potential is 0 within a small distance of x values within 0 to a. So, suppose along our x-axis, if I mark a point which is 0 and I mark another point which is a, within this duration, within this particular length scale, what do we have? The value of this potential is 0. So if I was plotting it, how will I plot? I will plot it, say, along this. This is 0, fine. But the moment I am crossing this 0 along this point, and I'm crossing or I'm reaching the point A along the x-axis, what is the value of the potential? It is as large as infinity. So how will I draw it? I will increase the value, and obviously it is going to increase till infinite values. So it is going to increase till infinite values. Along this value also, it is going to increase till infinite values. And not only that, please remember, anywhere else along the x-axis, this value is infinite. So only within 0 to a, the potential is 0. Elsewhere, potential is infinite. And now think, if there is a particle which is inside this particular region, say it is over here, will it be able to cross this high boundary and jump to the remaining positions? The answer is no, because elsewhere it has been acted upon by, or rather there is the existence of a infinite potential. So obviously any particle will not like to stay there and will always be trying to stay within a region where there is no potential. Now, feeling a little bit difficult to understand, let me give you an example, a real life example. Say, I have been given two situations, that I can live in a world where there are no forces acting on me, where there are no potentials acting on me. And there is another world where there is infinite number of forces acting on me. Which one will I choose? I hope all of you will agree with me that obviously we will choose to stay in a place where there is no potential, where there is no force acting on us. And the same thing happens for this particle as well. When it is getting a region within 0 to a where there is no potential, where the potential value is 0, obviously it is confined within that 0 to a. It cannot go beyond this, because beyond this boundary, beyond this particular limit, the potential is infinite. So as if it has been trapped within a well as in the same well that we use, the water well that we can think of. So if I'm dropped into a well, it is not easy for me to come out of it, as if I have been put inside a very deep well. In the same manner, a particle which is confined within this kind of a well is as if only present within the position 0 to a region. Elsewhere, it cannot be present. So have you all understood this part? Can you visualize or can you imagine what I mean by a one-dimensional potential well? The one-dimensional potential well means within a limit, what we have discussed here as say 0 to any length a, only here the potential value is 0. However, anywhere, any elsewhere positions, this potential is infinite, very, very, very large. And hence, the particle is as if confined within the region of 0 to a only. Right? Now we have to now solve the Schrodinger equation for such a particle which is to be found within this one-dimensional potential well. Fine. Remember, why do we use Schrodinger equation? We use Schrodinger equation to solve for this unknown wave function, because later on this wave function is going to help us to determine the other measurable quantities. Fine. So now let us begin with the solution, or how to solve the Schrodinger equation for this kind of a potential well. So if everybody has understood this, let me just go forward with the mathematics of solving the Schrodinger's equation. Fine. Now we will go back and write down the equation which is Schrodinger's equation. Right. So reminding all of you, if you remember yesterday's class, we write Schrodinger's equation as del 2 del x square. Now reminding all of you, this part is the kinetic energy operator, and along with it, when I write the operator of potential energy as V, this is our total energy operator in terms of kinetic energy plus potential energy. Now this operator will act on our psi and it will give us E psi. Again, reminding all of you that this equation that I have written here is the time independent Schrodinger equation. Remember, yesterday only we had solved the time part of the wave function, and the time part of the wave function is applicable for this system as well. So every day for every system, we do not solve the time part. We only solve the position part, and later on we combine it to get the complete solution. So today this psi that I have written here, this psi is only a function of our position x. It is a position dependent function only, and since we are considering a one-dimensional motion along x-axis, our wave function which we are trying to solve for is only a function of x. Fine. In this scenario, reminding all of you that doesn't this equation look like an eigenvalue equation? Just see, just notice this, that this operator is acting on the wave function, pulling out the energy value and giving us our potential and giving us our wave function back. So this energy, you will see that time and again we will come across equations which are nothing but eigenvalue equations. So our Schrodinger equation, the time independent Schrodinger equation in this form is also an example of eigenvalue equation. Fine. So now let us move forward. When I have written this, now we have to put the value of this potential as per our one-dimensional potential. Well, we already, yesterday when we had written this particular equation, I had told you that this V will vary from one system to the other. However, today we know our potential definitely from what I have already defined. So that very potential has to be used here or has to be put in here so that we will be solving for the wave function today. Fine. So now let us try to do that. But now all of you think and just try to realize the fact that we have already discussed on the fact that this particle which is confined within the one-dimensional potential well is not having any probability to be found anywhere along the x-axis, isn't it? It is to be found only within the limit of 0 to a. Why? Because only within this region that the value of the potential is less or rather 0, and elsewhere it has an infinite potential, hence the particle will never go there. And if the particle does not go there, the wave will not be present over there. Isn't it? I hope all of you are agreeing with me that beyond the limits of 0 and a, when I go to values less than 0 or greater than a, the particle will not go there. And if the particle does not go there, its wave function also will not be present over there. So this wave function that we are trying to solve today will only have values within our set region of 0 to a. Fine? Now, with this in our mind, let us try to solve the equation. Now see, when I am trying to solve for the wave function only within 0 to a, the entire solution of this equation also is valid only within the same limit 0 to a. Elsewhere, the particle is not present, the wave is not present, and hence the wave function also will be 0. So our headache actually has been reduced. We need not search it from minus infinity to infinity. All we need to talk about or all we need to calculate within this particular limit of 0 to a. Fine. So our equation, the value of this potential, we are going to put only within the limit 0 to a. Good. So now think, if you have written down the particular mathematical one-dimensional potential expression, we had the value within 0 to a, the potential was 0. Elsewhere, the potential was infinite. And since we are talking only about the 0 to a region, what is the value of v there? What will I put the value of v here? Simply 0. So within the limit where we are interested in, our equation has been reduced to only this much. Isn't it easy now? That instead of having the term with potential, because we have defined our one-dimensional potential of having the value 0 within our desired limits, the second term vanishes. And this is what is left from our Schrodinger equation. So all we need to solve now is only this part. So let me write it in a little precise manner. So this is what is left for us to solve. Fine. Now I hope all of you will agree with me if I just write it in a different manner, which is, see, do you agree with me when I write like this? All I have done is, because there was a minus over here, when we put them together, they become plus. And I have taken this h cut square. This h cut square by twice into the other side, and I have an equation like this. So is this equation okay? Very good. So now look at this equation little carefully. Now see, we are having a particular term over here, twice me by h cut square. What I will do here, I do not want to write this twice me by h cut square many times. I will give it a small name. What small name do I give it? Say I call this as quantity k square. Fine. So please note it down that we are replacing twice me by h cut square by a term k square. Fine. So what will my new equation look like when I have replaced this big term with a small k square? This is how this equation will look like. Now, if you look carefully into this equation, is it looking a bit familiar? Let me remind you. Let me show you an example where you will try to correlate this. d2x dt square plus k square x is equal to 0. Doesn't this equation, the form of this equation is just same as this equation? And remember, what is this? This is the equation of motion for a simple harmonic oscillator, where when I want to know how the position is changing with time, I solve this equation. So solving this equation, we get the value of x with respect to time, or we find out the time variation of position. On the other hand, what are we having here? We are having the variation. This same equation, this equation has the same form as this. However, here the unknown is our wave function, and we all know that we are trying to find out this wave function's position part. So we are going to get the function, this wave function as a variable of x, right? So see, we are now standing in a point of finding out or solving this wave functions, this space part, the position part only, right? And this is a very common equation, differential equation, and the solution of this kind of an equation can be generally, the general solution can be written as, see, this can have an equation, this solution as a sine function. This can have a solution as a cos function, or it can have a combination of sine and cos as well. Now, since we do not know whether it is only sine, whether it is only cos, it is better that we go forward with a combination of sine and cos. Fine. I will show you more in detail little later. So, this equation, when we have the differential equation of this form, the solution, the general solution of this equation can be written as a sine kx plus b cos kx. You all are much better than me in mathematics, so I hope all of you will agree with me when I write the general solution of this equation as a combination of sine and cos. So see, at this point, what I have received, I have already received the wave functions form as a sine kx and plus b cos kx, where what is k? Remember, k square is twice me by h cut square. So does this mean that since I have already received my wave function, my solution is complete? The answer is no. And why so? Because remember, even though I know this equation in this form, I do not know what is this a, neither do I know what is this b. So the solution of the Schrodinger's equation is not yet complete. So what we now will do is to find out these values, these coefficients of a and b, and try to figure out the entire mathematical expression for our wave function, or we will get the complete solution of the Schrodinger's equation for one-dimensional potential wave. Fine. Now, how do we find out? How will we get what is the value of A or what is the value of B? This is where we are going to use the boundary conditions. And remember, what is our boundary? Our boundary, one of the boundaries is at x is equal to 0 and the other boundary is at x is equal to A. So using those conditions, we will try to get the values of this coefficient capital A and this coefficient capital B. Fine. So shall we go? Yes, Arjun. Very good. You have written exactly what I was trying to say. So now using the boundary conditions, we are ready to find out these values of A and B. So if when I have this in front of my eyes, what I am asking all of you to do now is let's put the value of x is equal to 0. What am I putting? X is equal to 0. And reminding all of you about the boundary condition, or what did we define V as? 0 where 0 less than x less than A. So at a value which is less than 0, I have this potential equal to 0. However, when I am at 0, the potential is infinite. If the potential is infinite, the particle will not be present at x is equal to 0. And if the particle is not present at x equal to 0, the wave function also will not have the presence, and hence at x equal to 0, this wave function will reduce to 0. Fine. Did you follow my logic here? Did you follow the logic? Since at x equal to 0, exactly at x equal to 0, the particle cannot be present, the wave function also will not be present, and it will be giving us a value of 0. But this is what is our total wave function. So let us put in the values of x equal to 0 here as well. So when I put sine 0, obviously this term is 0. However, for cos 0, see I have the value 1. So what am I left with? B. So from here, what is the inference that I can draw? I can draw the inference that B is equal to 0, which means our second term is equal to 0. Now see, please remember this thing. Please understand this fact that A sin kx plus B cos kx is the general solution. However, when we are coming to our exact system where the potential is infinite at x equal to 0, this term cannot be present. Because in the beginning we did not know the entire situation, we had taken this term as well. But now when we have imposed our boundary conditions, we are seeing that this b is equal to 0. So if this coefficient is 0, the second term completely vanishes. So for our case, for the case of one-dimensional potential well, the second term need not be there, and we are only having psi x, the wave function is equal to A sin kx only. Right? So this was from the first boundary condition at x is equal to 0. Now, still our work is not done because A is not known. So we will go forward to see what we can do next. And what is it? Now we will go to the second boundary. And what is that? X is equal to A. Following the same logic as I had told you about x equal to 0, at x equal to A also, the potential is getting the value of infinity. So if the potential is infinite at x equal to A, particle will not be present there. And as a result, the wave function also will go to 0 in that position. And at the limit x is equal to A, at the condition, at the situation x at A, once again, wave function goes to 0. So this A sine, and now putting the value of x is equal to A here, what do I see? A sine Ka is equal to 0, right? Now I would like all of you to realize the fact that when I have written A sine Ka is equal to 0, it is as if the product of A into the sine function is equal to 0. So either A can be 0 or sine Ka can be 0. However, if I consider A is equal to 0, the entire wave function will vanish. So it is not a very plausible solution that we consider A is equal to 0. A cannot be equal to 0. So in that scenario, what will be equal to 0? The sine part will be equal to 0. So sine Ka is equal to 0. Now reminding all of you, when do we have sine is equal to 0? For what values of sine do we have 0? Remember, they are for sine n pi, isn't it? For all the values of pi, sine n pi, we can have the value equated to 0. Right? So when you compare these two results, we can write that n pi is equal to Ka. However, please see, what is this n here? What is this n pi here? These n are numbers. So when I have to put in the value of n, please remember this fact that n is 1, 2, 3 or any higher number. However, see, I have not written n is equal to 0. Why? Because again, if I write n is equal to 0, the entire solution will vanish and my wave function will vanish. And hence, for plausible solution, for physically significant solution, n values can only start from 1 onwards. Either 1 or 2 or 3 or any higher number, but not n is equal to 0. So from here, I can write the value k is equal to n pi by a, where n is equal to 1, 2 and so on. So taking this value of k and putting into our wave function that we were solving for, what can we write? What is the solution of our wave function? Psi of x is a sine n pi by a into x, kx, and k is n pi by a. So this is what we have received as our boundary condition results. Good. So now that we have understood, once again the question arises, you may ask me, ma'am, we have found out the value of k, very good, but then what do we have? Still a is unknown to us. So still the equation has not been completely solved. So now we will be solving the value of a. And this is where I would like all of you to remember the condition called normalization. Remember, we had talked in the note that I had given to you that there is something called a normalization of a wave function. Reminding all of you, how did we write normalization? Integration from minus infinity to infinity, psi star psi dx is equal to 1. Just a recap, psi star psi or mod psi square gives us the probability of finding the particle. And when we integrate this probability density over the entire range of space, we get the total probability. And since the particle is really present somewhere within the limit from minus infinity to infinity, the right hand side of this or the total probability comes out to be 1. This equation or this condition is called the normalization constant. Now, this very equation or this very condition is applicable for our wave function also. This wave function that we have received till now also, isn't it? So, if this is my psi, I can find out the mod psi square. I can integrate it over x and I can get equated to 1 on the right hand side. However, our life is not as complicated as searching it from minus infinity to infinity in our one-dimensional potential wave. See, just try to realize that when I don't know where the particle is, I will search it from minus infinity to plus infinity. And hence, I will be trying to locate the particle. However, in our one-dimensional potential well, what are we aware of? That the particle is present somewhere only within 0 to a. It is not beyond that. So, do I need to put the limits from minus infinity to infinity in this case? I hope no, right? So what will be the limit in our this particular normalization when we are working with our wave function? It will be only from 0 to a. So instead of searching the particle from minus infinity to infinity, our life becomes easy and we need to only put the limits from 0 to a. Since our particle has to be found somewhere only within 0 to a. Very good, Shrestha Arjun. You all are writing the right answers. I'm very happy. Now let us try to bring our wave function into this equation. Now look carefully. Our wave function that we have received, a sine n pi a by x, is a real function. There are no imaginary terms in this. There is no I in this. So when I find out the complex conjugate, a sine function will be a sine function only. I need not have any other complex number in this case. So what can I write for our case? Integration 0 to a square sine square dx equal to 1. Isn't it? Are you following me what we are doing? Now see, when I solve this equation, this part's value I can easily find out, and then this will help me to find out the value of a. And hence we will get the value of our unknown value a. Very good. Very nice. Very nice. So now when we are able to solve, if we can solve this equation, we can find out what is our a. Now since a is a constant, I could write it outside my integration. And I am now set to integrate this sine square function. Right? Now, you all must be remembering from your class 11, 12 days that when I have a sine square theta or a sine square x function, we generally reduce it. We lower the power to single power, which means I will not be integrating it as a sine square. Rather, I will take it to a cos 2 theta, right? To a cos 2. So, I hope you will agree with me if I write this as 1 minus cos 2n pi a into x by 2. So sine square n pi x by a, I have converted it to 1 minus cos 2 by 2. Am I right? Is my formula correct? Very nice. So now we are ready. So see, from one term integration, we can now divide it into two parts. So let me take this 2 outside. So we can now write this equation as dx minus a square by 2 integration over 0 to a cos 2n pi by a into x dx, and obviously the right hand side is equal to 1, right? So we can go forward. Now I will give you a very small good news. What is that? That this integration that you have over here, this cos twice n pi a integrated over 0 to a is equal to 0. Why this is equal to 0? I will give you a very small clue. I will not be solving this as such. It is not required for us. However, because cos twice of this function is an even function, and when we are integrating it over 0 to a, the value is going to be 0. So the second integration in our so-called solution is 0. So thankfully, what are we left with? We are left with only this integration being equated to 1. And when I integrate dx over 0 to a, what am I going to get? I will be getting only a. I am doing it correctly, I hope. So from here, can I not write a square as 2 by a, or the value of a as under root 2 by a? Got me? Fine. So here we are. Initially, we began with the unknown value of a, but by using the normalization condition, we have received the value of this constant amplitude a as root 2 by a. And hence, now we are ready to write our complete solution of the one-dimensional potential well as this. So, a particle which is confined within a one-dimensional potential well will have a wave function, the position part of the wave function to be this, right? Which is root over 2 by a sine n pi x by a. Now remember, what is this a here? This a, this entire wave function is dependent on the dimension of the well. We had defined the well within 0 to a. So larger this a, remember, larger this a, this wave function will have a different value. So This dimension of the well is very, very important, and the function that we are getting is sine, and this is how the amplitude of the wave function looks like. Now, I could say that we have received the solution and we can put a full stop over here, but no. While solving the Schrodinger's equation up to here, I am going to give you another bonus result, if you may call it. And what is that? Reminding all of you that what is this n pi a equal to? Remember, this n pi by a is equal to k that we had started with, a sine kx plus b cos kx. And from where did we get that k? Remember, k square was twice me by h cut square, where E is the energy of the system. So can I not write then that k square is equal to n square pi square by a square? And when I equate these two, what am I ready to get? What am I going to get? I am going to get the energy of this system, the energy of the particle which is confined within my one-dimensional potential well. So let me just take these values over there and see the energy of a particle confined within a one-dimensional potential well is n square h cut square. What was the other term? N square twice m a square and x square pi square and pi square. So this is how the energy of the one-dimensional potential well's particle looks like. But hold on, look into the value of this energy. This is again depending on which number? It is depending on the number n. And what are the number of n values possible? N or 1 or 2 or 3. Remember? So, please take a pause and try to think of the significance of this result. When I put the value of n is equal to 1 in this value, what will I get? I will get the smallest value of energy possible, which I may call as the, say, energy E1. And that value is coming out to be h cut square pi square by twice n square. Right? So this is the lowest energy the particle confined within the potential well can assume, can have. However, when I ask you that what will be the next energy it can have, the answer would be when I put in the value of n is equal to 2. So n is equal to 2 because we had an n square here, we will be getting a 4 in this case. So E2 is 4 times the energy of the first energy level, isn't it? So like this, I hope all of you will agree with me that E3 will be 9 because we are having an n square. When I put n is equal to 3, I will be getting an n times E1. So remember, this is where I would like to remind you about the Planck's hypothesis. Planck had told us that energy is not a continuous factor. It is not a continuous thing. Rather, it can only assume quantized values, discrete values. And see, the same result we are seeing in our potential well as well. The energy that that particle can have is either E1 or E2 or E3. The possibility of having any energy value in between E1 and E2 is 0. Anything between E2 and E3 is 0. So the only possible values of the energy are discrete values, as in terms of this quantity h cut square pi square divided by twice n a square. So isn't this interesting? So the same discreteness of energy value is received for our one-dimensional potential well as well. Correct? Now, in this case, n value, where is this n present elsewhere as well? Along with our value of energy, this n is in our wave function as well, right? Now, so see, when my particle is going to assume the value n is equal to 1, my energy value will be this. But at that time, please try to realize at that time when n is equal to 1 and the particle is assuming the value of energy as E1, what will be its wave function? Its wave function also will have n is equal to 1. So its wave function will be looking like this. So when the particle has the value of energy E1, I will call its wave function as say psi1, right? When I am changing the value, or rather the particle is gaining more energy and say it is having the energy of this, what will its wave function look at the time? The n value will become 2. Likewise, when I am changing this value to 3, what will be the wave function at that time? The wave function will be psi3 and this value will be 3 over here. So let us try to understand the significance of this. There is one particle which is confined within the potential well that we have defined. However, this same particle can have different energy values, and corresponding to each of those energy values, its wave function will be different from one another. The sign part will be the same. The function is having the same picture. However, its value is little different from one another depending on the energy it possesses. Remember, I was discussing it earlier as well, that the wave function of a particle is not unique. It can change depending on the system to system, as well as within a system it can change depending on the value of energy it is corresponding to. So what I can define, or rather I can summarize it as that when there is a particular energy of the particle, that energy corresponds to a particular wave function or a particular state in which the particle will be existing at that time. All right, please try to realize the fact that this wave function that now is changing with every energy level is corresponding to that very state in which the particle is. So when the particle is in the lowest energy level, remember we call the lowest energy level as the ground state. So when the particle is at the ground state, its energy is defined and its wave function is also defined. When this energy is increased, it acquires, say, it goes to the first excited level, E2 in our case, which we call it as the first excited level. Then the wave function also little bit changes itself and goes to sine 2 pi xy. Likewise, all these wave functions in the system are different for different energies, and the energies that we have received are not continuous, they are discrete. So this actually brings us to the complete solution of Schrodinger equation, where not only we have received the form of the wave function, we have also as a result received the value of energy. Remember, I had written in the very beginning and I had told you that isn't it looking like an eigenvalue equation? Just let me write it once again. H cut square by twice m del 2 del x square plus v acting on our psi is equal to E psi. So see, our total energy operator has acted on the wave function and has given us the value of this energy as well. So the Schrodinger equation was a form of the eigenvalue equation and the calculation has indeed given us the value of energy, right? So I would like to add a very small point over here that this particular operator, since this is the kinetic energy operator and this is the potential energy operator, the sum of these two operators is the total energy operator, but we call it by the name Hamiltonian operator. Please remember the name. We call this as the Hamiltonian operator. So when I write the sum of KE and PE operators, I call this as the Hamiltonian operator. Right? So the Hamiltonian operator acted on our wave function and gave us the value of energy as well. And in this process, we have not only received the value of energy, we have also solved who is this psi? What is this psi for our particular system? So this is how Schrodinger's equation helps us to find out our wave function and also to delve upon the value of energy for that corresponding wave function. Fine. So did we understand the today's lesson? Please give me some feedback that you all have learned with me. Hello? All right, fine. So thanks to all of you. So before I end up today's class, let me just give you a brief recap. Let us summarize what we have done. We have solved the Schrodinger's equation for one-dimensional potential well. And we have defined the potential well by the mathematical formula that it was 0 within the given limit and it was infinite elsewhere. The moment the value of x reached the value of x is equal to 0 or x is equal to a, elsewhere the potential took its value to be infinity. And starting from that potential, we have received the wave function form. Let me just write it in a generalized form. We write it as n. Right? This was the wave function that we received. And please note that since this function is depending on n, generally the solution is written as psi nx. Fine. And we have also found out the value of the energy for our one-dimensional potential well. Again, since it will depend on n, it can be written as n square h dot square pi square by twice n a square. So these are the two vital most results that we have derived today. So what type of questions might be given to you? Obviously, the entire derivation would be there, could be there. Or I could give you a very small sum, say like find out the energy difference between the second excited state and the first excited state. So remember, which one is the first excited state? When I write E1, that is my ground state. When I write E2, it is the first excited state. When I write E3, it is the second excited state. So if the difference of second and first excited states have been asked to you, all you have to do is E3 minus E1. And how do we get E2 and E1? We take this general formula, put the value of first excited state with n is equal to 2 and n is equal to 3 for the second excited state, and we will be able to do the mathematics. So like this, small little problems might be given to you as well. Right? So from here, the last point which I would like all of you to realize or understand is that this energy is varying with A. It is not that the dimension of the well is not important at all. The energy is inversely proportional to A square. So larger this dimension of the well, smaller be the value of the energy that the particle can acquire. So smaller the limit, 0 to A limit, as small this A dimension is, the energy will be. So this is where I would like to end up today's class. In case you have understood, very nice. And if you have any of the confusion, we will discuss it. Okay. Now Arjun is asking, it's totally like electron system. It's very close to the electron system. It is not exactly like that of an electron system. We will discuss. We do have the hydrogen atom in our syllabus. We will discuss. But this is, you can say, a mathematical, what to say. This is a way to make you understand that how Schrodinger equation can be solved. And this one-dimensional potential well is, what to say, an hypothetical situation. In real life, in real world, this will not be found anywhere. But this is very close to, as you are saying, that it is very close to a few systems that we can really have in our world. Okay, so that's all for today. Bye, all of you. Take care.